So it's my pleasure to introduce Professor Midolo from the Niels Bohr Institute at the University of Copenhagen in Denmark. So Professor Midolo completed his PhD in Eindhoven in the Netherlands, where he started working on quantum photonic systems, and then moved to the quantum photonics group at the Niels Bohr Institute, where he's been since. He was recently awarded the very prestigious ERC starting grant for his work, or to work on and develop circuits in sort of the nanoscale, so they live at the same dimensions that the quantum objects that he uses live on, but are actuated using motion. And of course, all of this has to be controlled electronically. And I think that this is what he's going to tell us, and we'll learn about why, what are the advantages, what's so special about these circuits, why are they so hard to make, and why is it so special, what he can do. And so with that, let me stop talking and let's start hearing from our expert. I hope you all enjoy the talk, and thank you, Leonardo. Please take it away.
All right, thanks a lot, Nir. Thanks a lot for inviting me and for the opportunity to present my research today with you. I would have liked to visit you as well in person. I guess it's still a little bit hard to do these days, but I hope to do it maybe in the future. And so welcome everyone to this seminar. So yeah, I would like to say something about the research I'm doing at the Niels Bohr Institute in Copenhagen. It's about these nanomechanical quantum photonic circuits, which is one of the examples here on the right. It's one of these nano photonic devices where you see waveguides and some mechanical structure. And I will get to this towards the end of my talk, where I will try to explain why this is needed and what is it good for. I set my presentation to be maybe a little bit pedagogical, in the sense that I was trying to introduce the field of quantum photonics itself. So apologies for those who are already expert in the field. Maybe this will sound a little bit already known to you, but I think in general it would be good to hear about. So here we go. So the main quantum system that we work with is a single photon. I think more or less everyone here has a notion of what a photon is. So we define it as a single quantum of electromagnetic radiation. And what we're interested in is actually its quantum mechanical properties. As you know, if I take a stream of single photons and I try to split it, for example, using a beam splitter, you see here, and I place two detectors at the output, what I get out from the measurement is that only one of these detector clicks at a time. And that seems to indicate that the photon is actually behaving like a particle that picks a particular direction after being splitted and impinges on one of the detectors, so only one clicks at a time. However, we also know that a photon is a wave, so if we don't place a detector at the output, then the quantum mechanics is telling us that the best explanation we have, at least for this phenomenon, is that the photon actually splits into two arms of this output, and it's simultaneously in both arms as a normal wave. And so this is the story of this wave-particle duality that's special about quantum mechanics. And also there is the concept that when we make a measurement, so we do an observation, we actually make the wave function collapse, we say. And so we actually reveal the particle nature of the photons. Now, of course, this leads immediately to this concept of quantum bit. And as you can see, it's very easy to implement in photonics, because all I have to do is simply to label my outputs as 0 and 1. And then I already have a superposition state of 0 and 1. My splitter is, for example, 50-50. And this is like the fundamental element that can be used for performing quantum computation, qubit. Now, of course, this is in stark contrast with classical bits, which can only hold a value of 0 and 1. Instead, a photon after a beam splitter can be encoded in an arbitrary superposition of 0 and 1. And potentially also a phase can be added to one of the outputs. So you can actually map the entire representation of a qubit into a sphere. So there are some immediate important technological applications that you can think about when dealing with this very simple experiment, which is just a beam splitter and photons. One of them is the generation of random numbers, of true quantum random numbers. And this has to do with the fact that the measurement that you have at the detector is completely unpredictable. So this two detector will generate a sequence of 0 and 1 that is completely randomized. And this can be used, for example, for generating secret keys or things like that. Even more interesting, and you probably heard of this as well, is the possibility to establish some secure communication between two parties. For example, Alice and Bob can communicate by encoding information in the forms of single photons. And now if an eavesdropper wants to listen to this channel, the eavesdropper has to introduce a beam splitter, most likely, to route some of the information, and then perform a measurement with some detectors. And this means that the eavesdropper will introduce some changes in the quantum state that Alice and Bob are sending. And if Alice and Bob are clever enough, they can actually figure out if somebody is eavesdropping, and therefore interrupt the communication. And this is based on the concept of no cloning in quantum mechanics, which is such that Eve cannot create a copy of a quantum state without having measured it first and having destroyed it. So this is a very intrinsic thing of quantum mechanics that we can exploit, for example, to establish secure communication. And I'm bringing this up because this is one of the reasons why here at the Niels Bohr Institute, we are very much interested in the photonic quantum technology. You probably heard that there are a lot of implementation of quantum technologies. But photons are particularly interesting because they enable communication. And this is an example of a project that we are running right now of communicating using this secure quantum channel between two parties. So this is a map of Copenhagen, the greater Copenhagen area. We are located here. This is the Niels Bohr Institute. And here are our colleagues, our partners in the project at the Danish Technical University. And actually between the two of us, there is a fiber link that is already in place, and it's used for regular communication, the regular internet. But we can take some of this fiber, some of this channel, and actually send single photons in them, and implement some sort of quantum channel between us. It's just to show that photonic quantum technology is actually very close to practical application, and it's not just an abstract theory that lives in the lab. This is part of a project that is called FireQ. It's really about showing that the single photon quantum technology are already pretty much field ready, so it can be already deployed in the field for practical applications. But of course, you can go beyond the simple idea of encoding a qubit and doing 0 and 1. You can actually start to do some logic. So you can do some operation between the qubits. So if you could, for example, build a sort of quantum gate, you could start to do operation between, let's say, two qubits. So let's assume we have a gate here that takes these 4 channels in, and 2 represents a qubit A that can be 0, 1. The other 2 represents 0 and 1 for qubit B. And then this quantum gate is performing this operation. So if A is 1, then you flip the value of B. Otherwise, you do nothing. So some of you have probably recognized that this is the famous controlled NOT gate. It's one of the most important gates. It's called C-NOT. And you can see here in this very simple example how it's supposed to operate. You send a photon in 1, and the photon gets flipped and exits at the other port 0. But now it becomes very interesting, this gate, when you start to operate with states that are not in a 1 or in a 0, but actually in a superposition of 0 and 1. For example, if you put a beam splitter here at the input, you create a superposition of 0 and 1. And so what should the quantum gate be doing now? Now, the thing is that you have to understand that A is 1, and therefore B has to become 0. But A is also 0, so B has to stay 1. And so what comes out is that the 2 photons are now potentially null for channels. And this is now very hard to visualize in practice. And this state is a very particular state. We call it an entangled state. This is why sometimes the C-NOT gate is called entangling gate. And this entangled state can be written like this, as you can see here. And it's basically telling you that if I ever make a measurement now on qubit A, for example, and I find out that it was at 0, then this branch of the code executed, right? And then the other qubit must be necessarily 1. And vice versa. If I measure 1, then the other one has to be 0. So this very particular state now means that the two photons that are now in all these channels simultaneously are no longer separable from each other. They are indeed entangled. And this becomes very interesting because you can start to think to share this entanglement at longer distance. So you can take these two photons that you have previously entangled in place and actually send them farther away from each other. And that entanglement will remain for a very, very long time, and also very, very long distances. And so whenever it performs a measurement somewhere, immediately the other photons get projected into the state as predicted by quantum mechanics. And so an application of this, which is a little bit farther ahead in the future, is to build photonic quantum networks. So this is something we're actually working quite extensively here at the Niels Bohr Institute. It's as I said, it's at the very beginning, this idea, but there is already, at least in Europe, an initiative to establish the so-called quantum internet. And the vision here is to say, let's have quantum computers that can operate locally in many different nodes, but then can be entangled with each other through a photonic link. So this would actually, let's say, allow us to probe also some interesting and fundamental aspects of the nature, which is how large can you make an entangled system and how delocalized you can make it. So it's actually very, very interesting. And of course, it has practical application for simulation and computing, because you can use these massively entangled systems to start building more advanced quantum, simulating quantum systems that you could not simulate otherwise classically. Okay, now comes the problem. How do we build a CNOT gate in photonics? Now, this is not easy because photons do not interact with each other, typically. So you can just get two photons that come close to each other. They typically do not interact. So you will not be able to perform this flipping of the bit that I mentioned before. However, you can do something if you have photons that are perfectly indistinguishable from each other, so perfectly identical. And it's based on this concept of quantum coalescence. And so imagine you have two photons that impinge on a beam splitter from two different inputs. Now, the two possible outcomes are only that the photon come out on one side together or on the other side also together. The probability that the two photons are simultaneously reflected or transmitted cancels out. So this does never happen. Now you can use this phenomenon, which is a quantum interference phenomenon, to build complex logical gates at the expense of having to add some detectors into your circuit. So I don't want to go too much in the details. This is actually a proposal that came out in the early 2000s by Neil and Neil Bohr, and it's quite famous. But you can actually build a CNOT gate using only linear optical component and single photon detector. So it's actually very nice because even if we don't have access to this nonlinear interaction between the photons, you can still build a relatively large system that performs entanglement between different photons by just adding linear optical component and detectors. Now, if you take a step further, you can actually generalize this concept to the idea of having many photons that interfere with each other in a large network of beam splitters. Now we're scaling up this idea of just one beam splitter and one photon source, and we're taking many identical single photon sources, and we're trying to make them interfere into a large network with many modes of beam splitters. So it's basically a very large interferometer. And it turns out that to predict the output of this experiment is actually very complicated for a classical computer. And it becomes harder and harder the more photons you put into the system. And actually it has been calculated or estimated that for around 50 photons have to be completely indistinguishable. The output is not solvable even on the fastest supercomputer. Now, this maybe is not a particularly interesting application in itself of a quantum computer, but it just tells you like what the power is of building a photonic quantum computer in this way. Of course, now a passive network of beam splitter is probably a little bit useless, but you can actually make it programmable. So if you have a way to control each individual beam splitter here, for example, its reflectivity, its transmittivity, the phase shift that it introduces, if you have tools to program this from outside, then you can really implement any unitary transformation that you want to have. And this can perform potentially arbitrary calculation using the photons that you have here. And this is used a lot, for example, in quantum simulation, where you're mapping some particular property of a quantum system, for example, vibration in molecules, to a particular mode into this interferometer, and you're calculating its time evolution by running it into this device. Now, most of the experiments that are done nowadays typically run on free space setups, like the one you see here. This is just a picture I took randomly from the internet. It just shows one of the typical quantum optics laboratories this day, which with a lot of free space components, mirror, beam splitters, and potentially you can implement all these quantum gates and functionalities free space, like you can see here. Free space means just that light is traveling in air or in vacuum instead of in a guided system. Now, of course, this is very hard to scale. If you had to implement more and more functionalities, you will need probably more space, more money, more time, and most likely you will run out of all of these before you manage to scale this technology further. So this is why there is a lot of interest worldwide to do actually chip scale integration of these functionalities. Now, this is a lot in parallel with the fantastic development that there was with that we witnessed with electronic integrated circuits, which started with really a few discrete components glued together into a common substrate, which nowadays can be scaled up to millions and millions of logic gates integrated to the same chip. This is now what we have today. So can we do the same with photonics? And the answer is absolutely yes. This is already happening, not necessarily in the quantum area. It's happening also in the classical photonics area. Actually, this is a big drive there, mostly for classical telecommunication. But the process has been the same. So you start from discrete optical components, laser, mirrors, splitters, and so on. And you miniaturize everything and you implement everything inside an integrated circuit, which is now a photonic integrated circuit, no longer electronic integrated circuit. And you can really implement hundreds and hundreds of these functionalities all within a very tiny area. And so making a technology that is way more scalable. So what about quantum? So also quantum technology can benefit from photonic integrated circuits. And here I'm showing an example of such a quantum photonic integrated circuits. This was developed at MIT, if I'm not mistaken, by a group of dear Kendall. And it represents a large multi-mode interferometer like the one that I've shown schematically before, with a lot of programmable gates, which are all controlled through these external electrodes out here. And if you zoom in, you actually see these white areas here that are the waveguides. And you see some active tuning elements. For example, this is a Mach-Zehnder interferometer, 2 50-50 beam splitter, and a phase shifter in between. Now, this phase shifter operates with a phenomenon called thermo-optic effect. So you apply a current to flow into this electrode, and you heat up the waveguide. And by heating it up, you change the refractive index, so the optical path changes of this arm, and you are switching the output of the light. So you can build an arbitrary reconfigurable splitter. And so with these controls, you can actually take any qubit and rotate it in the Bloch sphere the way you want it. So this is very nice result. But the circuit in itself is sort of incomplete. What it's missing is the actual quantum features, which are the single photon sources, which are not integrated in the circuit, and the single photon detectors. And that's basically the start of my story. So how do we combine all these things together in a way that can be seamlessly integrated and and compatible with each other. As we will see, it's not so easy. So let me start saying a few words about these single photon emitters. What are they, and how can we use them? So perhaps the most famous single photon emitter is just a simple atom. So here it's just super schematic. And you know there are discrete energy levels which are quantized for electrons, and by having transition of electrons between different atomic orbitals, you can have emission of energy or absorption of energy. So typically the way you operate with an atom or any other quantum emitter is that you excite it with some light typically, and you promote an electron from an inner shell to an outer shell, so an excited state. And then the electron decays and emits just one photon at a time. And for most atoms, this transition happens typically in the visible, near infrared wavelengths. So we're talking about low energy optical wavelengths type of photons. Now, this transition also corresponds classically to transition dipoles. So classically, you would treat this problem as a simple linear dipole. So if you want to visualize exactly how a photon looks like when it's emitted by a dipole, then it looks like a wave that propagates in all directions, right? And it's only when you put a detector that you reveal exactly where did the photon go. But this is actually how the photon radiation would look like. So you can already see that working with atoms is a little bit difficult, because you will need to be able to collect all this radiation somehow and bring it to a place, for example, your detector, in a sort of very efficient way. This is not, of course, very easy if you don't capture somehow the photons that are emitted by this dipole. And so in our group, we actually work with a different type of emitter, which is not directly an atom, but it's a solid state artificial atom, which is called the quantum dot. And you can see an image here. And I should mention that this type of emitter has been investigated a lot by my colleague Peter Loader, who is the leader of this Center of Hybrid Quantum Network that I mentioned before. And so what are they? They are basically little islands of indium arsenide, very tiny in size, surrounded by gallium arsenide. Indium arsenide is a low bandgap material, as you can see here. And it's surrounded by another material which has a much larger bandgap. So what it does is basically it forms a very tiny quantum well here, that with a confinement that it's all in all 3 dimensions. So it's not just like a simple quantum well, which would be just a 1D confinement, but a 3-dimensional quantum well, so a quantum dot. And by having this 3-dimensional confinement, what you get is that you start to have discrete energy levels, as you can see here, that resemble a lot, and in fact are conceptually identical to the shells of an atom. So you can have an S shell, a P shell, a D shell, and so on. And the way this operates is very similar to an atom. So you excite it optically, you generate electron hole pairs inside the gallium arsenide, and then this electron hole pair recombine inside the quantum dot. And since these transitions are discrete, they actually generate just one photon at a time. And typical emission wavelength here, we're talking about 930 nanometer, so red, near infrared, red infrared. And it typically operates at cryogenic temperature. Here, I would like to stress this fact a little bit, because many people think, can I make an emitter that works at room temperature? It's actually very hard, because at room temperature, you have a lot of mechanical motion, you have thermal excitation. And so all these levels are actually blurred, because this quantum well is shaking continuously, right? So you cannot really operate in getting distinguishable photon from an emitter at room temperature. So you typically have to cool it down, to remove most of this phonon background, and actually improve the quality of single photon emission. I would still like to mention that we're not talking about millikelvin, which is typically needed from some quantum technologies. So here you can live quite well with 2, 3, 4 Kelvin temperature that is easily achievable in a normal helium refrigerator, helium-based cryostat, or closed cycle cryostats. So the kind of technology that allows to operate quantum dot is actually improving a lot, and it's becoming more and more affordable. Now, another interesting thing about quantum dots is that the transition dipoles that represents how the dot emits light are very well known and can be determined in advance. And they're two, basically, orthogonal to each other, and they're in the plane. And that's a very important fact because it allows me to engineer my photonic nanostructure, as you will see in a while, knowing already very well in advance how the dipole are oriented. And so if you look at the typical gallium arsenide wafer, that's where we have a lot of these quantum dots. You cannot see them because they're extremely small. But we know how these dipoles are oriented once we find a quantum dot. So we know how to align our nanostructures to it. So this is now an artistic view of how these quantum dots look like. So unfortunately, there is some drawback with the quantum dots, which is the self-assembly. So self-assembly means that the quantum dots nucleate randomly. So it's basically you're trying to grow a material that is not compatible with the substrate. So indium arsenide doesn't like to grow on gallium arsenide because it has a different lattice constant. So it either prefers to nucleate into tiny islands, which are our quantum dots. And unfortunately, this process is random. It happens randomly into the chip. However, if we can control the density well enough, then we can still isolate a single dot and do operations with it. So we can access it from the top, excite it, and get the photons out. And of course, if we do that in a bulk material like this one, all the photons will be emitted in the plane of the wafer and probably most likely towards the bottom of the substrate. We won't be able to efficiently extract the photon out. And again, because we're talking about dipoles that radiate in all directions and preferentially now towards the substrate being having the highest index of refraction. So what we do to control where the photons are emitted is we start fabricating waveguides. And here you can see such a very simple waveguide. It's just a rectangular nano beam with a rectangular cross-section, which is very small. It's just enough to confine a single mode of radiation. So you can see the electromagnetic wave simulated in such a nano beam. And the quantum dot couples to this mode, exclusively to this mode, and therefore radiates photons exclusively in this direction. And this is what I said before about the orientation of the dipole is very important, because knowing that the dipole is oriented in a particular direction, it allows me to orientate these waveguides in such a way to maximize the coupling between the emitter and the waveguide. In fact, we can get extremely large quantum dot to waveguide coupling that are very close to unity. And this is an important result because this beta factor that you see here is a figure of merit of how deterministic my single photon source is. And deterministic means that every time I have an excitation in the quantum dot, I emit a photon, and that photon is coupled to a waveguide mode that I know, that I can control, and I can manipulate from that moment on. So here I am with my single photon source with quantum dots emitting photons into a waveguide that now I can use in my circuit. So now we started the NBI developing this gallium arsenide waveguide platform, which is a suspended platform, as you can see here. And the reason why it's suspended is that we really want to maximize this coupling between the quantum dot and the waveguide. And we suspend it using tethers that do not disturb the optical mode, but actually keep it suspended, but actually keep the waveguide suspended all the time. And we can also add the electrical control on the quantum dot, and this is a very important thing. And you can do that by slightly doping this membrane. So this is actually something you can do during the epitaxial growth of these structures. You can add dopants. And so you can build, for example, a PIN junction here. And so when you apply a voltage to this PIN junction, you're applying an electric field to the quantum dots. And that is very beneficial for the quantum dot emission because it reduces all the noise that is coming from, for example, random charges that are around the quantum dot. But also very important, it allows for the electrical tuning of the excitonic transition, so for this electron hole pair. So let's say you have a quantum dot that emits at 930 nanometer, you want to bring it to a different wavelength, then you apply a field and you tune this emitter to a different wavelength. So that gives you another knob to to control your quantum dot. This is very important, especially if you want to build several quantum emitters and you want to have them all in resonance because you would like to build indistinguishable single photon sources. So we have written a lot of literature about this. And actually, this single photon source is becoming quite good. We also have a way to fabricate our chips so that to have local controls that we can have multiple devices which have individual controls, so we can control quantum dots independently from each other and potentially scale it up. So this is how the state-of-the-art single photon source looks today. You can see there is the idea is to have like a waveguide. This is a particular kind of a waveguide. It's called a photonic crystal wave. I don't want to enter too much in the details. But the concept is very similar. So you excite with a laser from the top, you come with pulses and excite the quantum dot, and the quantum dot re-emits single photons, and the photons are collected through another grating outside. And actually, you can get extremely large fluxes of single photon and with very, very high quality. I will come back to this figure of merits in a second. Now, this is a method for generating single photons, but this method is not really scalable in the sense that it's hard to, for example, make 2 or 3 or 4 of these quantum dot sources. That's because you will need a laser, pointing to each of these devices. So what we have invented is actually a new kind of circuit that allows you to excite the quantum dots through the waveguide. So again, it's a little bit long to go in the details, but the concept of this circuit is that you simply need to excite with your excitation laser somewhere here in this grating coupler. The light will be going into this waveguide, and we reach the quantum dot, and then it will leak out. While the quantum dot generates the photon, and the generated photon will actually stay into this waveguide and be collected here. So this very particular device allows you to perform a sort of plug and play single photon source. So you just plug it from an input and an output. So you send input laser photons, on the output single photons from the quantum dot. So how do we quantify the quality of the single photon sources? Basically, we do the experiments that I already mentioned. The first one is called technically Hambury-Brown and Twist experiment. So you send a single photon, 50-50 beam splitter, you try to split the photon, you put 2 detectors at the output. And then if it's a true single photon source, the 2 detectors should never click simultaneously. So if you take a correlation, a spectra between correlation between this photodetector, what you should observe is that at 0 time delay, there are no clicks. And that's exactly what you see here in this data. And then by looking at the ratio between this amplitude of these peaks, you can extract what we call the purity of the source. So a very highly pure source is a source that is made indeed of only single photons and does not contain multi-photon states. And then another important figure of merit is the indistinguishability that I mentioned before. So here we do, again, this experiment where we have, we're trying to interfere 2 photons. So we're getting 1 photon here and 1 photon there. And as I mentioned before, if they're truly indistinguishable, you will have 2 photons coming out this way and 2 photons coming out this way, but you will never have 1 and 1. So these 2 detectors, again, should never click simultaneously if they're purely indistinguishable. And what are we interfering here? It's a little bit special. So we are getting just 1 quantum dot, and we're sending many single photons in the input, and we are interfering a photon arriving at a time, say 0, with a photon arriving at a time tau. And we are adding delay, and so we can compare how indistinguishable a photon is that was generated now from a photon that was generated, I don't know, 100 nanoseconds later or more. And so we can actually interfere up to 115 photons that arrived afterwards and still observe very high indistinguishability of these photons. So the visibility of this experiment remains quite high. And so this means that we can generate a stream of hundreds of photons that are all indistinguishable from each other. And so this becomes a very interesting resource to do these experiments that involve demonstrating quantum advantage. Now, I would like to open a small parenthesis about something that we have done very recently that I'm actually quite happy and proud of. We've also shown that we can use, we can generate these photons at telecommunication wavelength. So the quantum dots, as I mentioned, produce photons at 930 nanometer. 930 nanometer is not a good wavelength for telecommunication because light gets absorbed a lot in a fiber. I think the loss is around 3-4 dB per kilometer. But if you could work at 1550, which is the typical telecommunication wavelength, then this absorption will go down and you will have losses in the order of 0.2 dB per kilometer or so. Now, unfortunately, it's not easy to do this, but you can do it with a nonlinear process, which is called three-wave mixing. And what you have to do is basically to provide the missing energy, let's say, that of the photons through an external pump. So you basically get a laser that works at this very particular wavelength, 2325. You mix it together with this photon, and what comes out is photons at telecommunication wave. You need a particular material which has a particular nonlinear coefficient. It's called lithium niobate, and to get this to work. But actually, it works extremely well. We got very high efficiency of conversion. So 42% of the photons get converted to 1550, and I think it can be improved further. And we recently published this work. And I think what is remarkable here is that the visibility of these fundamental experiments, so the indistinguishability of the photons, is preserved after the conversion, which was not trivial at all. So after converting the photons from a wavelength to another, you still have indistinguishable photon at the output. And that's actually very interesting because it means you can really establish some sort of quantum communication that is also based on coherent photons. Okay, so now let me come to the point of what my research is mostly about, which is combining the sources and the circuits. So as I mentioned, we have these very nice circuits in silicon, but they're missing sources. On the other hand, we have these very nice single photon sources that are on a different material platform in gallium arsenide and operate at cryogenic temperature. So mixing the two is actually a little bit difficult. And one of the biggest challenges is actually what I mentioned at the beginning, which is the possibility to perform these controls on the chip. So these silicon chips operate with thermal phase shifters, as I mentioned, thermal devices. But thermal devices are not compatible with cryogenic devices. That's because they just stop to work. To say that the thermo-optic effect, so the variation of refractive index due to temperature, becomes basically zero at cryogenic temperature. So you cannot use anymore the thermal phase shifter for when you start to integrate the source and operate at cryogenic temperature. So yeah, it's not an easy task to integrate. So we need to find a way to build controls like this one that use some different mechanism that is not based on thermo-optical effect. So this is just another way of stating the problem. We have a single photon source in a waveguide, and we would like to have some way of controlling where the photon goes. So that's something like a router. And it should be able to switch between the two waveguides within a reasonable time. Here we say 1 microsecond. That's typically the time during which the quantum dot emits coherent photon. As I showed before, you can generate streams of 100 photons. So that's sort of the relevant time that we are interested in, relevant time scales that we're interested in. And it should be compatible with cryogenic temperature. So there are many ways of doing this, but none of them seem to be really compatible with a single photon source. And then it turns out there is actually a very nice solution that is relatively simple, which is to use mechanical motion. So imagine just having a mirror that can be moved, can be rotated, and that can steer the beam from one input to the other. And so this is just the sort of conceptual idea behind it. And so the idea is to introduce some sort of nanomechanical functionality in the quantum photonic circuits that we have. Because if we could do that, then there would be no problem with temperature and no problem with interaction with the single photon source. So I'm interested in investigating this area. And actually, what I'm developing is part of a broader set of devices, which are called generically nano electromechanical systems. And the idea here is that you are coupling together sort of 3 degrees of freedom, the electronics, the mechanics, and the optics. And as you probably know already, if you can build a very nice electromechanical system, so devices that, for example, by applying an electric field, produce an electrostatic force and move some particular object, or vice versa, like the mechanics moves and produces a change that can be sensed by some electronic circuit, for example, moving capacitor plates. And on this side, you can also recognize some of the optomechanics work. Now optomechanics has become a very important field. The mechanics can, for example, move mirrors and tune the resonance of a cavity. But you can also do the opposite. So there can be optical forces that actually push mirrors and bend a mechanical object, right? So these fields are investigated in parallel. Actually, if you bring everything together, you can actually start to realize systems where you can directly couple the electronics and the optics together. So you can generate an effective electro-optic interaction mediated by the mechanics. That's sort of the idea behind. And I've written extensively about this. If you're interested, you can also have a look at this perspective article on electromechanical system. Why nano? Nano is interesting, especially when it comes to photonics and nanophotonics, because all the relevant scales are indeed at the nanoscale. So the fields are confined within nano distances. And as I will show you in a second, this effect can become quite large and sizable when we are dealing with nanomechanical effects, so at the nanoscale. So just some example of works done by several groups on, for example, tuning a beam splitter just by controlling this cantilever. Here you apply an electrostatic force and you move this cantilever up and down, and you can control where the light goes. Here is a photonic crystal cavity that you can tune. So you just move this membrane up and down, and you can you're tuning the resonance of this cavity. And so this has been shown to be also compatible with quantum emitters, which is also very important. So it operates at cryogenic temperature, and it's compatible pretty much with all materials. So it's kind of a material agnostic approach to tuning and reconfiguring devices. There are a lot of other benefits. I don't want to list them all, but for example, it's very low power dissipation. It's just a capacitor. So it operates with nanowatt power typically, unlike thermal optic phase shifter, which really consume a lot of electrical current and indeed can heat up the entire circuit, so dissipate a lot of energy. So let me give an example of these mechanical devices. For example, a gap variable directional cathode is the most famous example. And the idea is simple. You have two waveguides that are very close to each other. Here, the nano distance is very important. And they're close enough so that their confined field actually leak a little bit into each other. So when you send light into one waveguide, it starts to move into the other waveguides and vice versa. And now if you're changing the distance between the two waveguides, you can control how quickly this light transfers from one place to another, from one waveguide to the other. And this way you can control actually where the light comes out. This is just a simulation that shows as a function of the waveguide separation how much intensity is being transferred to one port or to the other. And you can see how strong this effect becomes when you come to very, very small distances, like you're coming to the 50, 60 nanometer distance, and just 10 nanometer motion is enough to switch light completely from one side to the other. It's actually quite impressive. So we have built a device like this, and this is the one I was showing at the very beginning. This is fabricated in the same platform that I was showing you before. And what we have realized here is indeed couplers and waveguides, and then everything is suspended with tethers, and there are quantum dots in it. And then light enters into this region, and if you zoom in, you actually see there are two waveguides here that are very close to each other, 150 nanometer apart. And there are these two sets of electrodes here on the right and the left that are biased to a particular voltage. And as soon as you do that, you apply a force, and this force pushes the two waveguides apart. And so you can control the distance between the two waveguides and tune this device on the fly. So these are some of the experimental results. They're exciting. For example, one input port here, light travels through this, and then we are measuring the ratio of intensity at the output. So we're measuring the splitting ratio of this beam splitter. You can see that it fluctuates between minus 20 dB to plus 20 dB. So that's the full extinction of the device. And this is tunable. It's tunable as a function of the voltage that we apply. So the larger the voltage, the more we are changing this displacement. You can actually see from a cross section here that we're able to fully switch this device from one state to another with just about 60 nanometer displacement. So very, very tiny motion, very low loss and very low power consumption. And we can do that with quantum dot as well. So we can identify a single dot, excite the dot, and then look at the output again and see what comes out. And actually what you see now is the sharp spectral lines that actually are single quantum dot transition that we're looking at. We can just look at one of these and actually trace the behavior, and we can find similar splitting ratios, similar extinction. And it operates very well, and it's compatible with the quantum dot. And we can actually see that these are a single photon by performing this Hanbury-Brown twist experiment. So to our knowledge, this is one of the first, if not the first, single photon routing that is done on the very same chip with the emitter. And so this is a very important step forward to develop this technology. And we're taking this concept now beyond that. We can also realize other types of devices, for example, tunable filters. Here you can see an example. It looks quite similar, but here instead of having just two normal waveguides, you actually have a photonic crystal. So you can, photonic crystal cavity. So it's a little resonator. You can tune in wavelength. And what it does is basically acts as a color filter. So it can select exactly one color at a time. So as the light travels, you just pick one color, and this color is transmitted and the rest is reflected. So it can be used, for example, also for making integrated spectrometers or things like that. Yeah, so this is basically what I'm working on right now. I think this project has just started, so it's about seeing how much we can develop here and how much we can integrate single photon sources and level of scalability we can achieve and how many of these devices we can implement into the same circuit. It will not be easy, but I think it would be quite exciting to do, and potentially it would be solving a lot of existing issues that we already have. So let me just also acknowledge the team that works with me and especially my collaborators. So for the growth of the quantum dot and the materials that you have seen, this is the work of Arne Ludwig, is really a hero from the University of Bochum, and he's growing this very, very nice quantum dot material. And also on the quantum dot physics, I collaborate with Richard Warburton and University of Basel, and of course with my colleague Peter Loder at MBI. And thank you all for your attention, and I'm really happy to take questions if you have any.
Thank you very much, Leonardo, for a really nice pedagogical but also state-of-the-art talk. It's a really nice summary.
Thank you.
The old and the new. So maybe I wait a second to see if somebody else wants to unmute themselves or turn on their camera and ask something. Oh, Stephen, please, just go ahead. Oh, you're still muted.
I will echo Niels' sentiment and say thank you for that excellent talk. I had a question on your indistinguishability is very high for a waveguide with no cavity filtering. You didn't mention if there's any spectral filtering, but at least you have imperfections from the transmission and reflection of the beam splitters, multi-photon background effects, and intrinsic phonon coupling effects. Yes. So was your number without any spectral filtering, which I find hard to believe, or did you have a narrow filter there? In which case, what is the real indistinguishability without filtering?
Yes, so the reported values that you see, this 96, 97% is always corrected for the imperfection of the beam splitters in the Mendel experiment. And it's also corrected for finite G2 of 0. And now we are sort of debating on exactly how this correction should be done precisely.
So that's what I don't understand. How can you correct for an intrinsic multi-photon background?
That depends a lot. Yeah, that depends a lot also on what is the origin of this background. If it's if you are accidentally repumping and so you have a multi-photon emission from the dot itself, or if it's a laser background. And so in this case, the correction is slightly different. But there are some theoretical models on how to correct for that. And normally we do a generic correction, just taking the value of G2 of 0, but that's not, as far as I know, the most precise way of doing it. You will really need to identify which contribution comes from where. But it's true in the literature, it's generally accepted to do a correction with H2 of 0. But normally we also report, I have to say, also the raw indistinguishability that you just measure from the experiment as is.
Okay, and that's without spectral filtering or not?
Oh yes, these are done with spectral filtering. You always put an etalon to remove phonon sidebands.
Okay, so the indistinguishability is taken a hit, yeah.
Even if you do, let's say, resonant excitation, you have emission in the phonon sideband, so you need to filter that out. And that's the reason why we started developing also on-chip filters, mechanically tunable, because when you start to come with multiple photons and multiple sources having to place filters everywhere, or multiple filters in free space, then it's sort of, yeah.
All right.
Bring us back to the point of how much you can integrate and how much you still need free space elements.
Okay, maybe. Oh, Connor, did you want to ask something?
Yeah, I'd love to. I don't know if my connection is a bit spotty, but I'll go for it.
I can hear you well.
Great. This is definitely a lower level question, but I was wondering if there are any consequences for using fields to modulate the mechanical control, like if that will affect any of the other uses on the chip or in the local region of any other processes that are happening on the chip or near the chip, if those fields will influence those at all.
Let's say now we are looking into, it's a good question, thanks. In generally, we say that this is not the case because the fields, let's say, let me see if I can go back. So let's say here, I would say the electrostatic field is mostly localized within these two gaps, so far away from the optical region where the waveguides are. So we probably estimate that some stray capacitance, some stray fields can still be in the proximity of the gallium arsenide. That per se is not a big problem. But if you have strong electric fields on a semiconductor, you can have electroabsorption, which makes it, so basically you're making the material more absorptive than what it is, especially close to the material band gap. And since we're not that far, actually, this is a potentially an annoying problem. But we have not seen this here because indeed the fields are really far away. They're not they're decoupled from the optical region.
Thank you.
Jacob, please.
Hi, thank you for the talk. I just have a quick question, and sorry if I missed this somewhere in there. I'm just curious, how many quantum emitters have you been able to use like simultaneously on the same integrated chip? And what are the challenges with scaling up these systems and adding more quantum emitters?
No, thank you. I didn't really talk much about this. It's a very good question. I think, so right now it is indeed a challenge to have multiple quantum emitters that can be all integrated with each other. It's something we are starting to do only very recently. So we have recent work that shows that we can probably do 2 for now. But you know, 2 is already a good step, and in particular, if we can make it in this way, so with this, with this approach that I was showing here, because a device like this one potentially could be scaled. You could have several of these, and you can drive them all through waveguides. So you just use a single excitation spot and drive this light and distribute this pump over different emitter sections. Of course, you will need to individually control the emission energy of each of these emitters. So having all these emitters to be emitting at the same wavelength, otherwise they're not indistinguishable. So there are some practical challenges there. And as I mentioned before, there is this concept of self-assembly, right? So the quantum dots are nucleating at random position, at random wavelengths. And so controlling and finding dots that are exactly identical to each other is very hard. So this is why we need local gates, controls, and this is a lot of work also on the fabrication side, but we are working on this, and indeed we are about to we're writing something right now about making 2 of these on the same chip, and potentially this can go further. But I want to say also that another approach that we are pursuing right now is just to use one emitter, and if you want to have all the photons in parallel to enter in an interferometer, you could also do something called spatio-temporal demultiplexing. So you take a stream of single photon and you use an array of switches to route each photon into a different channel. So for example, you can say a 1 to 4, and every photon, there is a set of switch that routes the photon from, say, output 1, output 2, output 3, output 4, okay? Now these 4 photons will come at different times, but you can put some delays, but you have to do it off chip, of course, because these delays have to be quite long, potentially, and delay the time of arrival. So all these 4 photons would arrive simultaneously. And this would still work because indeed all our photons generated by one quantum dot are indistinguishable with each other. So with the proper multi-channel demultiplexing, you can already generate a multi-photon resolve state that is good for potentially quantum, for example, boson sampling experiment or things like that. But there are, let's say we have these 2 parallel tracks, right? The multiplexing is one possibility. The other is on the chip, try to scale up the sources and have multiple emitters that emit indistinguishable photon. This second direction is a bit harder to implement in practice, but it's, I guess it will come eventually.
Thank you.
Thank you. Very good questions. Is there another one? Okay, maybe I can ask a quick one. Yeah. So you talked about a lot of different aspects. There's, the speed that you're going to do this, the complexity of each device, scaling things up. What do you see as the bottleneck currently for this technology, and what do you think is the bottleneck? Like, what's the hardest challenge to overcome right now, and what are the things that you think you've really got under control?
You mean in the nanomechanical?
Yeah.
Which is, I think probably one of the hardest things is to realize a fully tunable phase shifter, because what I've shown is, okay, in the gate language, this device here is implementing this Rx of theta. So it's a rotation around the x-axis of the Bloch sphere. It's exactly, if you look at the transfer matrix, that's exactly what it does. Now, if you want to do also rotation around Z, that you will need for an arbitrary qubit operation, you need a phase shifter. And this will be a little bit harder to implement, I believe. So this is something that, I mean, I'm supposed to realize, but I don't have a super clear answer right now on how to do it. But potentially a similar compact phase shifter will be needed at some point to do a similar thing. The other difficulty is integrating all this technology with this is more like a very detailed fabrication aspect, but it's important, is integrating all this with this PIN controls that I was showing, these electrical gates. And the reason there is that the best single photon sources that we have at the moment that are useful for quantum computation are implemented in this PIN. But this circuit that I'm showing here, I didn't mention it, it's not made on a PIN junction. It's a small detail, but from the fabrication point of view, makes things very, very hard. And I had a student who tried to do this for quite some time. It was very difficult to do. And so this is potentially another issue that I don't think it's not solvable, but it's challenging. Probably a lot more near, but that's what I can think of right now. Yeah.
No, I see that Connor has another question.
Yeah, sorry. This once again might be a little bit outside of the area where the bulk of this talk happened, but I was wondering, in the quantum dot formation, when you're growing the dots, how long is the growth process? Like at what point? Because in my mind, there's always like the first particle that's going to stick to, like, for the rest to nucleate onto. Like, what's the time frame on the growth process?
I should say that I'm not an expert in growth of quantum dots. I've not grown myself. So I rely a lot on collaborators. As far as I know, it's not a particularly long process, but I cannot give you an exact time. So growing the full stack of the wafer potentially takes several hours and maybe half a day. I don't know. It depends on how many layers you want. I think it's mostly like waiting time to settle the temperature. It's a very complicated process, you know, finding out what is the exact temperature that you can get the condition for growth. And the way it works, as far as I understand, but I'm going a little bit in uncharted territory for me, is that you start growing indium arsenide, right? You switch from gallium arsenide to indium arsenide. So you have these indium atoms, arsenic atoms, and they start to nucleate. And at the beginning, you form a very thin film that's called the wetting layer. So the first film actually deposits. It's like a quantum well. It's everywhere. But this film has accumulated a lot of strain. So the subsequent atoms that are joining, and I think that happens in, I really don't know what the time scale there, but I believe it's a matter of seconds. And as this layer starts to grow, then they don't really form another layer. So it doesn't grow epitaxially, but it starts to grow in this nucleating into these little islands that you have seen in the slides. And then it's really a matter of regulating the time and the temperature and the conditions until you stop the process and switch to gallium arsenide growth again and restart the growth of the capping of these emitters. Sorry if I can give you a more precise answer than that.
Thank you.
Okay, with that, let me thank Leonardo, and I will then stop recording the talk. And if somebody wants to stop and talk a little bit more informally, I'm sure Leonardo would be happy to stick around for a few more minutes. It's late in Denmark, so we promise not to keep you for too long. So thank you very much, Leonardo.
Thank you. Thanks, everyone.